So today we're going to be talking about dependency grammars and dependency parsing. So first, some motivation and some definitions. One of the basic ideas of syntax is that words don't stand on their own. They're connected by some hidden structure that connects the words to each other. The goal of dependency parsing is a fairly minimal representation of the connections between words, as pairwise connections between words, connecting heads to the dependents. This is what we hope to uncover from text. We want to discover which words are heads and which words are dependents. For example, modifiers, objects, complements. Here's an example sentence labeled with dependency arcs. Verbs are connected to its objects. And we also have this hypothesized root that sits all the way on the left-hand side that has as its child the main verb of the sentence. And you can also see the notion of phrases in here. So if you look at what is a root of various subtrees, and here, by beating Sri Lanka is rooted by the preposition by, and so this represents a subphrase. But the question is how do we choose these edges? Some very high-level rules for when D is a dependent of a head H in a construction C. If the head determines the syntactic category of a construction and can replace the construction, so if you have gray dogs, you can just replace that by dogs. If H somehow gives the semantic specification of C and the dependent specifies H, so if you have a gray dog, that's a kind of semantic specification of what kind of dog you have. The head in a construction is usually obligatory. The dependents can often be optional, so this again is the example with gray dogs, you can remove the gray. H often selects D and determines whether D is obligatory. Selectional restrictions are an example of this, so you can eat food, but you can't eat chairs. This is saying that the head, the verb eat, specifies what kinds of objects can be used in this construction. The form of the dependent also depends on the head. So for example, in Romance languages, you have inflected adjectives. What form the inflection takes depends on the case, the number, the gender of the head. The position of the dependent in the sentence also is specified with reference to the head. So for example, in English, our adjectives come right before the noun they modify. In some Romance languages, it's the other way around. In many cases, it's clear which direction the relationship should go, which is the head and which is the dependent. In many cases, it's clear which word should be the head and which word should be the dependent. So for example, the modifiers of verbs and nouns, those are obviously dependents. The object of verbs, also obviously dependents. Other cases are trickier. So for example, complex verb groups. If you have a construction like can see, which of those should be the head? In this case, we'll say that helper verbs act as the head. Another tricky case is subordinate clauses. We'll use the convention that the word that introduces a clause acts as the head. Similarly with coordination, if you have two words joined by a conjunction, is the conjunction the head? What we'll do is say that it follows a linear order, that if you have A and B, A will be the head, the conjunction will be in between, and the second object in the coordination will be the child of the conjunction. This is fairly arbitrary. Prepositions, we'll assume that the preposition itself is the head and the object of the preposition is the dependent. Punctuation, this is really arbitrary, we'll say that it's related to the main verb of the sentence. So more concretely, the problem of dependency parsing is taking an input sentence and then giving as output a graph that connects the words together. And we'll talk about some of the constraints on the kinds of graphs that you can generate, but in order to do that, we need to introduce some notational conventions. So first, we need to introduce the idea that a word is connected to another in an unlabeled dependency, and we'll represent that with a right-pointing arrow. Another concept that we'll need is undirected connectedness. Is there an edge going in either direction between two words at positions I and j? We'll represent that with a left and right pointing arrow. And we'll also want closures of these relationships. So is there some sequence of edges going from I to j with some intermediaries? We'll call this an unlabeled closure. Similarly, is there any connection between words? We'll call this an undirected closure. Can you get from I to j with some sequence of edges going in either direction? Okay, so given these notational definitions, we can now say what are valid dependency parses, what are valid graphs, given an input sentence. So we want syntactic structure that is complete, that is, all the words are connected. We want a hierarchical structure. We don't want cycles in our graph. And we also want each word to have at most one syntactic head. And we'll also enforce connectedness by adding the special root node that I showed you before. These are the intuitions for the conditions that will place our dependency graphs. But let's go through these conditions a little bit more formally. We say that the graph is connected. That is, for every two words, there is some sequence of edges going between them. That is, you can't have two independent subtrees. It's acyclic. If you have an edge going from I to j, then you can't go through some other sequence to go back from j to I. That is, you cannot have a circle anywhere in your graph. We also say that it's single-headed. If I has j as its dependent, then there can't be some other node claiming j as its dependent. And finally, many parsing algorithms assume that the parse tree is projective. That is, if you have an edge from I to j, then anything between I and j can't have an edge that goes outside of I to j. This is easier to see with an example. So here is a non-projective example. So a hearing is scheduled on the issue today. The edge going from scheduled to today crosses the edge going from hearing to on. And so this makes the sentence non-projective. Given this visualization, you can see that the definition of projectivity is equivalent to having a planar embedding of the graph. And so most theoretical frameworks don't assume projectivity because it's needed for free word order and long-distance dependencies. In some languages like Czech, a very high percentage of the dependencies are non-projective. However, in English, it's not so big of a deal, and it can lead to some simpler algorithms, and faster algorithms too. So the algorithm that we'll discuss later in class is actually projective, but there are non-projective algorithms out there, and they're fairly common. Okay, so now let's talk about how you can do dependency parsing. So there are many algorithms out there. We're going to focus on one specific example, an arc-factored projective model. And we'll talk about what that means in a second. These are fairly common assumptions, but not universal ones. So what does it mean for a parsing algorithm to be arc-factored? So first, we assume that there is a scoring function that tells us how good a particular graph is. And we'll assume that the score factors over the edges in the graph. So that is, the score only depends on individual edges present in the graph. So it doesn't depend on, say, pairs of edges. It only depends on single edges, and you have some function psi that tells you how good is that edge. In this class, we'll make a further simplification that will ignore the labels on the edges. So it's just, there's some score that tells you how good is it that you have an edge between word I and word J. And you can think about this probabilistically. If your function psi is actually a probability, you can think about these terms as log probabilities. And so remember, if you have some probabilistic expression where you're multiplying some things together, if you take the log of it, it's just addition in log space. We're going to use dynamic programming in order to solve this problem. And the reason we do this is that we want to avoid reanalyzing substrings because the substrings are independent problems. And dynamic programming is a tool that we can use to exploit this independence. If you've seen chart parsing in linguistics, it works on a similar principle. Once we have a solution to a subproblem, then we can remember it and then solve the overall problem by composing these subproblems. And in this particular case, our subproblems are going to be stored in a chart, somewhat like what we did with part-of-speech tagging, and we're going to store in this chart what is the best possible score that we could get for particular subtrees. And because there are many different combinations of parse trees that explain our sentence, we will implicitly consider all of them and choose the ones that give us the best overall score. So like the Viterbi algorithm, we'll solve subproblems to find the overall optimum score. And the central idea is that we're going to use spans. These spans encode what is the best possible score that you can get for trees going from one position in the sentence to another position in the sentence with a particular orientation. Instead of thinking about specific edge configurations, we're going to consider equivalence classes of edge configurations that have a particular head of a subtree and go in a particular direction. So we don't want to think about all of the different configurations. Instead, what we'll do is we'll lump them all together in spans. That as long as you have your head at position I, and you are directed in the right direction or the left direction, it's the same thing. And we only want to consider the best possible combination of edges that have that configuration. An additional distinction we'll make is whether you can add on additional edges to the frontier of these spans. And so we have 4 different kinds of subtrees. So we make 2 distinctions: direction and completeness. So a tree can have either a left direction or a right direction, and a subtree can either be complete or incomplete. So let's talk about that and the notation that we'll use now. So a span is characterized by 4 things. 1, a start position. What is the leftmost word in this span? 2, its start position. What is the rightmost word in the span? 3, the direction. If you look at the subtree, the edges have to start from the root of the subtree. Do the edges go left or right, starting from this root? And the final and 4th characterization of the subtree is it complete or not? Can it accept additional edges? We'll get a 4-dimensional chart that stores all of the possible subtrees for the sentence with these components. So this is very similar to the 2-dimensional tree that we did for part-of-speech tagging. Inside each cell of this matrix, we will store a score for that span. Okay, so let's look more specifically at the 4 types of trees we can have. So a right complete span has the form ST right complete. And so this means that the root of the tree is at position S. And it can have an arbitrary substructure until word T, but word T can't have any additional children. A left complete span is the mirror image of this. So you have a range going from S to T, where T is the root of the subtree, and you can have arbitrary edges up until word S, but word S cannot take additional left children. A right complete span will represent as this trapezoid, and the root is at S, and it can have arbitrary edges up until T, but T can take additional right children. And the left incomplete span is a mirror image of this. The root is at T, and you can have arbitrary substructure until word S, but word S can take additional children. What's the intuition of what we're doing here? The entry in the chart at 0L right complete should contain the best score for the overall tree. So this requires us to take a divide and conquer approach to solving this problem. So we have a right complete tree. How can we break this up? So what this amounts to for the entire sentence is usually finding out where is the main verb. And so once you find the main verb, you can break this up into subtrees and then find out the best way to construct those subtrees. So once you figure out where the main verb is, you now have a right incomplete tree for the first half of the sentence and a right complete tree for the second half of the sentence. And these problems are independent. We can find out what is the best way of arranging edges in these spans that give us the entire sentence. So on the first half of the sentence, once we have the right incomplete span, we can break that up into what are the right children of the root and what are the left children of the main verb, and how do I add an edge going from the root to the main verb. And we can figure that out, and then we can recurse on the subcomponents there. Similarly, for the second half of the sentence, we need to figure out what are the right children of the verb. This problem, breaking up a right complete subtree, is equivalent to the overall problem of figuring out the parse tree of a sentence. So this is recursive. So let's go into a little bit more detail about how we can fill in this chart recursively. When we have a left complete span, these are formed by adding an edge between two complete subtrees. So if you want to form a left incomplete span, you add an edge going from T to S, where T is the root of a left complete subtree, and S is the root of a right complete subtree. And there are many ways to do this, and so we find the best possible scoring configuration of edges where we're adding an edge going from S to T. The right complete span is the mirror image of this. We're adding an edge from S to T, where S has a right complete subtree and T has a left complete subtree. And this is why it's dynamic programming. When we compute the score for any span, we consider all possible ways that the span could have been built. And this is represented in the max operator in this rule. When we're considering right complete spans, it's quite a bit simpler. Here, all we need to do is find a right incomplete span and a smaller right complete span and glue the two together. This is basically saying we've finished the job with merging things together and we just need to complete them. And the left complete span is the mirror image of this. The only thing that we haven't talked about is the base case. And the base case is simply that every word is its own complete span with score 0. And so what we do to complete the chart is we can combine segments. Let's say that we join a couple of complete segments together to create incomplete spans, and this adds edges. We can then complete these spans to create right and left complete subspans, and then join them together with an additional edge that creates a left incomplete span. We complete this span, and now we have a right complete span and a left complete span. We can add an additional edge going from the root. This creates a right complete span that goes over the entire length of the sentence. But we're not done yet, because what we're interested in is a right complete span going over the entire length of a sentence. So this is how you can merge subspans together to create a complete parse tree. And we'll work through an example numerically in class. And again, to reiterate, you look at the cell corresponding to the span that goes from 0 to the length of the sentence that is complete and directed to the right. This is the best parse score that you can get for your entire sentence. And remember, you need to have breadcrumbs in these dynamic programming algorithms in order to build up the entire tree, and you know what choices you made while building up the tree. There are many extensions to the dependency parsing models that we presented here. First, you don't have to assume a completely arc-factored model, and in many cases you don't. So for example, you might want to add in dependencies upon siblings and grandparents in the tree. For example, saw with telescope is more likely than bridge with telescope. And you can figure this out by having a relationship between grandparent and the grandchild. So saw telescope is a more likely combination than bridge telescope. Similarly, you can add in sibling relationships so that fast sports car is more likely than fast slow car. You can also use other frameworks completely in order to figure out the optimal parse tree. So for example, graph algorithms allow non-projective sentences. And there are other models that use sequential processing where you move left to right in the sentence to build up your parse tree. These are a little bit more psycholinguistically possible and actually perform quite well in practice now. You can read more about these in the book Dependency Parsing by Kubler, McDonald, and Nivra. This is available for free online. I encourage you to check it out. There's a link on the course webpage. So finally, let's wrap up by talking about where you get the score function and how do you know whether you're doing a good job of parsing a sentence or not. So where does this attachment score come from? We just assumed that we have the psi function that tells you how good an edge is. So one way of doing this is just treating it like a language model, but it's operating on vertical spaces rather than horizontal spaces. So given some example parse trees, you can ask how likely is the noun bagel the child of the verb eat. If you haven't observed that combination, you can back off to what is the probability of a noun being the child of the verb eat. And if you don't have any of those observations, you can back off to a noun being the child of a verb. So very similar to the language model problem that we saw before. You can also train models with discriminative approaches, and this minimizes the overall errors that are made in your parse tree. So that begs the question of what does it mean to make an error? So how do you score whether your parse tree is correct or not? Well, you can ask how many sentences are exactly correct, but that number is probably going to be pretty near 0. And it's not necessarily informative because it disguises tiny, insignificant errors from getting the complete sentence wrong. So what we want to do is look at something a little more atomic than that. And so what we usually look at is edge accuracy. How often do you get the correct head to dependency link with the correct label? So this is the labeled attachment score. And slightly more forgiving than that is the unlabeled attachment score, where you're simply asking, do I have an edge going from the right place to the right place? And finally, you can look at the label accuracy. So how many tokens, how many words did you apply the correct label to? This is very similar to the part-of-speech tagging task. Another thing you can do is, if you're using your parse trees for a downstream task like information extraction, you can ask, how well are we doing on this downstream task? This typically tends to give you numbers that you care more about rather than these abstract edge accuracy.